So let's talk a little bit about intellectual humility and belief revision. We've established that explanation has a unique benefit on learning, and explanation is part of this process. And we know that revising beliefs or revising explanation is at the core of intellectual humility. After all, in order to be humble about what you know, you have to be willing to be wrong. You have to be willing to revise your beliefs. Now, examining constraints on explanation, I think, provides insight into the process of belief revision. What kinds of context and information motivate children to revise their beliefs? Right? This is a crucial part of understanding how the development of intellectual humility proceeds. So we know from Karl Popper that observation is always selection. It needs a chosen object, a definite task, an interest, a point of view, a problem. When we generate an explanation, we're always looking to explain something in particular, right? We're not interested in explaining everything. So a big part of what I want to understand and what I've studied is what motivates children to explain, what piques their curiosity. This is crucial to understand how to get children to revise their beliefs. We have to get them to engage in understanding in the first place. We know that explanation is a selective process. We also know that, like adults, children aren't interested in explaining everything. They're not curious about everything. Children are much more curious about some things than others. And if we want to optimize learning, it follows that we should know a lot about what children are curious about, what piques their curiosity and their interest. And examining what motivates explanation provides insight into the process of scientific reasoning and belief revision. So let's talk a little bit about what kinds of events motivate scientific reasoning, and in particular, motivate children to construct explanations. We know that children explain events that have the potential to teach them something new. So in particular, inconsistency with prior knowledge triggers children's explanatory reasoning. Children are much more interested in explaining an inconsistent versus consistent outcome. And the quality of their explanation, the sophistication of that explanation for an inconsistent outcome is greater than for a consistent outcome. We've also shown that children's explanations guide their exploratory behavior. So the way children explain outcomes influences the sorts of behaviors that they engage in to test whether their explanations are accurate or not. We know that children preferentially explore inconsistent outcomes that they have explained. So there's a dynamic process between explanation and further exploration. So I think explaining inconsistency is in fact a really crucial mechanism for learning. Inconsistent outcomes pique children's curiosity, motivate children to generate explanations, which subsequently guide their exploration and hypothesis testing behavior. This generates new information, which feeds back into the kinds of explanations that they generate and the process by which they revise their explanations in response to inconsistent or new information. So to do this experimentally, we control children's expectations and beliefs. So let me give you an example of how we've done this using novel stimuli, these light boxes. So to do this, what we've done is we present children with outcomes that are consistent with prior knowledge, as well as outcomes that are inconsistent with their prior knowledge. We present those outcomes simultaneously to children, and then we ask them why. Why did that happen? To do this, we use a novel task with novel causal properties and categories. Now, the benefit of this design is that we have a number of different measures of children's explanation. We can measure what they explain first, the content of their explanations, and how their explanations influence the kinds of exploratory behaviors that they engage in. So here's an example of an experimental task that we've used. We use these novel light boxes and novel objects with novel labels. This is to introduce new information to children and to prime what their expectations are. So first we have a training trial, the TOMA training trial. And here we put a TOMA on each of the boxes individually. And what you see is that TOMAs appear to activate the box. They turn the light box on. Next, we have a training trial for blickets. And here we place the blicket on each of the objects, again, independently. And as you can see, the blickets do not appear to turn the light box on. Next, we have a trial where we simultaneously place one toma and one blicket on each box. As you can see, the toma activates the box exactly as you would expect, and the blicket does not activate the box. And we ask the child, why did that happen? Then there's another trial where once again, a toma and a blicket are placed on each of those boxes simultaneously. And what you see here is that the blicket does not activate the box. Again, totally consistent with what you would expect. But in this case, the toma does not activate the box, which is inconsistent with your expectation. And once again, we ask the child, why did that happen? And following that explanation, we give them an opportunity to engage directly with the objects. So once again, we can analyze what they explained first, the content of their explanations, and the kinds of hypothesis testing behaviors that they engage in their attempt to understand why that inconsistent outcome doesn't appear to work.
Nothing. This one's lighting up and this one's not. So that means what's making this light up?
And what we found is that explanation guides exploratory behavior. Children preferentially explore inconsistent outcomes they have explained. Children also are more likely to first explain that inconsistent outcome, suggesting that inconsistency piques children's curiosity and motivates their explanations.
Oh, it's because this needs to be like this, and this needs to be like that. That's why. Oh, probably the boxes are the wrong way.
We also found that causal explanation and exploratory behavior work in tandem to guide hypothesis generation, or the generation of explanation, and subsequent exploratory behavior, or hypothesis testing.
Oh, because the light goes only to here, not here. Oh, the bottom of this box has electricity in here, but this doesn't have electricity. It's lighting up. So you need to put 4. So you need to put 4 on this one to make it light up and 2 on this one to make it light up.
So what you can see here is the interplay of inconsistency, explanation, and exploration. You can see that this child respond to inconsistent information, and in that process generate multiple different potential explanations that he then explores or tries out. When faced with information that's inconsistent with his expectation, he revises his beliefs and tailors his exploratory behavior to understanding new outcomes. And there's an iterative process here by which inconsistent information, explanation, and exploration are all working in an interconnected way.